Now one thing, this is where it starts to get a little confusing, right? Because I did everything here in terms of the A phase, in terms of the A phase, right? Because we're only doing one phase at a time. But don't forget, we wrote a Kirchhoff voltage loop along the A path, giving us this equation. We plug these values in to this equation, giving us our answer. Okay? But we actually have two other phases. We have two other Kirchhoff voltage loops. Okay? So if you wanted to be thorough, what you would do is you would go and look at this one and plug in these values. So VBC is going to be VBN minus VCN. And you would do that calculation. And then you would take CA. You would say that VCA, which is the other line voltage, you would take CN, take this one, and subtract AN, which is this one. So you see, each one of the phases has a unique subtractive relationship with the line to neutral voltages. You can just plug them all in and do the exact same calculation with all the exact same complex arithmetic that you get, and you would get a relationship between BC and it in the line to neutral voltage, and CA and its line to neutral voltage, okay? I don't really want to do all of that because I don't think it really adds a lot to it. So I'm not going to do all of the math, but I am going to show you the punchline, and I'm going to summarize it in a chart. So for other phases, you get the following. You'll get VBC is equal to VBN minus VCN. That's the other equation that we had there. And then we'll just plug in the values that we had that I just showed you. It would be V phi at an angle of negative 120. Minus V phi at an angle of positive 120. So again, you could do it using the long drawn out, complex arithmetic, magnitude, phase, and all that, or you could just put a 1 in your calculator and stick it in there and see what you get, and use it as a generalization like that. And what you will get is VBC is going to be equal to, shouldn't be a big surprise, square root of 3 times V phi, but the phase angle you're going to get when you do this is not going to be negative 30, it's going to be negative 90 degrees. Now, you might be worried because you say, well, wait a minute, this is negative 90. The other one we got was positive 30. Now I'm starting to get confused. Okay, just hold on for a second. I'll show you how everything lines up in just a minute. This is what you get for the BC phase. Okay, now let's do for the third one real quick. Again, I'm skipping a lot of the steps because I'm trying to connect the dots for you. CA, the equation, the original equation from the Kirchhoff voltage loop was VCN minus VAN. And then we plug in the values that we had here. It's going to be V phi at an angle of 120, positive 120 degrees, minus V phi at an angle of 0 degrees. So again, it's a different subtraction. And when you put it into either into your calculator or you expand it all and do the magnitude phase, e to the j phi, cosine plus j sine theta, all that stuff, you get VCA is going to be equal to, again, square root of 3 is always the common thread here, V phi, but this phase angle is again different. It's positive 150 degrees. So what this is saying, and I'm going to summarize it in a chart, but what this is saying is, take a deep breath with me, okay? For the A phase, the line-to-line voltage is equal to square root of 3 times the line-to-neutral voltage shifted by 30 degrees. For the B phase, its line-to-line voltage is the same square root of 3 times the line-to-neutral voltage, but it's shifted by negative 90 compared to its line-to-neutral voltage. In the C phase, is you take the line to neutral voltage times square root of 3, but you shift it by 150, positive 150. At this point, you should start to become a little bit concerned. How am I going to remember all this? When is it plus 30? When is it this? When is it that? Well, we're going to address that right now, and we're finally going to wrap up this whole section, believe it or not. But in order to do that, I need some space. So what I'm going to actually do is sacrifice this beautiful drawing that we've been using for a while. We're going to sacrifice it because we don't need it anymore. We've grown out of it, outgrown it, I should say. And then we're going to draw this master table, which is actually going to serve you throughout the rest of this class. So this is what we call a summary. Okay, for the positive ABC phase sequence. Only for the positive ABC sequence. I have to deal with negative sequence in another section for you. But this is for the positive ABC phase sequence. What do we have? All right. We have something called a line.